Uh, Hello everyone, I'm Jacob Rogers, and I did a spectroscopic analysis on HV UMA. Well, as we've seen from some of the earlier presentations, the physics of light is quite fundamental to all sciences. The way that we describe it by its wavelengths and energies is essential and builds the foundation for spectroscopy. We can look at the absorption and emission of light from atoms, and this can give us fundamental information about the objects that we're observing. In particular, for stars, we can see what it's actually composed of, the general temperature and sizes, and even the magnetic fields that arise from these stars. I've included a spectral plot from HV UMA. The wavelengths are given along the horizontal axis, where the shorter wavelengths are found further to the left and the longer wavelengths are found to the right. So in the plot you can see the continuum, which is kind of just a blurring of all wavelengths. And then the absorption lines are characterized by these dips within the continuum. So some stars are special in that they vary in their light. We've seen some of the pulsating types, which we call RR Lyras. However, there is another type, which is the eclipsing binary or rotational. This is due to the obstruction of light that we can actually observe, and if it's periodic, then we classify it as an extrinsic variable star. So a binary star system is just a system of two stars. You can generally see them through a telescope or high-resolution binoculars if the distance that separates these two stars is large enough. But if they're close or they have fairly dim luminosities, you have to turn to other methods to analyze these systems. So the eclipsing binary system is actually kind of common to us. We can think of it as just one object eclipsing the light from the other. And this is usually characterized by its light curve, and it has two minima, and the sizes of these minima depend on the sizes of the stars and the distance that's separating the two. General nomenclature for these stars is to call the brighter star the primary and the dimmer star the secondary. If they have equivalent brightnesses, then it's just kind of an arbitrary choice. So an interesting property of binary stars is when they get close together, they can actually physically touch one another or have a very small distance that separates them. They share energy and matter through what's called a Roche slope, and it can be seen in the GIF that's provided. It's the general area in between the two stars. These stars are usually eclipsing binaries. They are characterized by their short periods. They're highly elliptical components, and due to their close proximities, they have equivalent temperatures and brightness minima. So spectroscopy of eclipsing binaries can be quite difficult because the absorption lines from the two stars just kind of combine, and it appears as if it was just from one star. However, if the conditions for the system are just right, then we can actually see the Doppler effect happening between these two stars, and it shifts the wavelengths as one of the stars is moving away from us and the other is moving towards us. This can be seen in this plot from a binary system, Beta Auriga. In the middle of the plot, you can see the characteristic dips from the two wavelengths, where the left is from one star and the right is from the other star. And near the bottom of the plot, you can see the combination of the two wavelengths. So in my star system, HV UMA, it was initially classified as an RRC pulsating type. It was relatively recently determined that this classification was wrong. So through photometric and spectroscopic analysis, they determined that it was actually a low mass contact binary, which is a very rare category for stars. Its prototype star, which it's based off of, is the W Ursae Majoris. It has a very low mass and a short period. So this short period was most likely what caused its initial classification for a pulsating type star. The radial velocities of the system is unusually high, which is part of why this category is so rare. And due to the contact nature of these two stars, the luminosity minimum are fairly equivalent. So the star is a spectral A type, which means that it mainly consists of hydrogen and contributes to its relatively high temperatures. So we obtained data from the DAO over a 3-year span, and from this data, we plotted the flux and analyzed certain absorption lines that stood out to us. Looking at the hydrogen lines, which were most prevalent, didn't really give us a lot of information and had already been done before. So under the advice of Professor Barnes, I went looking for boring lines. There weren't really boring lines through a closer look, because I zoomed in on the magnesium absorption lines, and I thought I saw the characteristic Doppler effect happening between these two stars. So I had to filter the data because it was really noisy and kind of hard to interpret. I've included a subplot that shows the filtered data on the left and the unfiltered data on the right. These two phases can show that sort of characteristic splitting of the spectral lines of these two stars. We decided to go in and analyze this further by looking at the wavelengths. It was an arbitrary choice to choose which was the primary and secondary, so we just chose the furthest to the right as the primary star. We went in and performed a quadratic fit, which is essentially just a parabola, and the vertex of this parabola we determined would be the most accurate wavelength for the system. Using these wavelengths, so using these wavelengths, we were able to determine the relative radial velocities. We had to use the relative velocities because there was a shift in our spectra that we believe was caused due to the data reduction techniques that's used by the DAO. We had to use the relativistic Doppler formula for radial motion, and we took averages from the characteristic lines that appeared in both the magnesium and the calcium absorption points. The data table on the left shows the values that we found, and the data table on the right shows the determined velocities from Sack and his team of astronomers. The final plot here shows the relative radial velocities versus the phase. The brighter of the two points are the values that we found, while the darker orange correspond to Sack's values. There are some inconsistencies with the values, but we're quite happy with how it turned out, and this moderate success gives us hope for further analysis of this very unique binary system. Thank you. Yeah, are there any questions? Yes?
So I suppose I could have asked this earlier, but can you elaborate further on emission and absorption?
Yeah, so certain atoms absorb very specific wavelengths of light, and this is due to the energy that travels with those wavelengths of light. It's kind of the classic case of the Goldilocks. It can't be too high and it can't be too low. If it's just right, they'll absorb that light. And once they're kind of bored with this light, they just send it off in all directions, which is actually why the sky is blue.
So is it the light could come from nuclear fusion in the center of the star?
It could be, yeah. Or it could be from really anywhere that's producing light. Yeah. Yes?
So in your last cut, it seemed like there was one point that was down much lower. It seemed
Oh,
like
yeah.
an outlier. Do you have any thoughts about why that sort of separated from all the other data?
That point was kind of the bane of this entire analysis. That was actually from Sachs' team. I'm still not entirely sure how that value came about, but there are some interesting theories that kind of arise from it, such as like a coronal injection that caused a mismatch in the light that they were observing. But really, we don't know. Yeah.
Do you know how they finally determined and classified the stars correctly? Because it seems pretty likely that why they would have thought it was our line in the first place.
Yeah. So in the hydrogen lines, they had very specific phases that showed sort of that Doppler effect, but it was very minor. So Sachs' team decided to perform a Gaussian sum on these hydrogen lines, which kind of gave information from two different characteristic curves. They were able to go in there and say that the furthest to the left was due to the secondary and the furthest to the right in these sort of splits was due to the primary. And they determined the temperature, and then from that temperature they kind of worked backwards to figure out the general luminosity that they were looking at and how it varied. And from the light curve, they just kind of went from there and found the radial velocities. Yeah. Well, thank you.